Good day to you on June 4th, 2026 from Galactic. Over here you'll see our list of terms that we're using to coordinate an approach to continuity. One of the most important concepts ever revealed in science is the notion or concept of continuity. Simply defined, it's the opposite of quantization or particularization. Continuity implies no separation, whereas in the notion of, for instance, atoms or any other objects that we consider to be physical objects, they're separate. Objects are not connected to each other. However, at the cutting edge of the philosophy of science, which is where science seeks to get, where it transcends science itself to reach human conclusions, the notion of continuity is now at the very top of the list. Bernardo Kastrup has done an amazing piece of work over a decade now. He has been producing a framework which is quite simple in its conceptualization, the way we phrased it. It's a notion of continuity to describe the physical world. In other words, everything is connected. David Bohm also came to the same conclusion. And in effect, so did Roger Bošković, although he was dealing with particles, which necessarily must be separated. What Bošković was able to show, and I was able to prove using the spherical geometric approach, is that his notion of indivisibility and continuity are in fact dualistically related, so that both are true at the same time. This is the nature of the paradox that confronts the human mind, which needs to adjust to a new framework for universal space. The use of the word space here is the extended or most abstract use of space, the geometric usage of the word space. There is such a thing as spatial space, which is the normal connotation, of course. But a geometric space may not necessarily be spatial, and this is the crux of the matter as I have decided it. I've made several breakthrough discoveries in mathematics and algebra and geometry, such that there is a nonEuclidean basis for mathematics now, which could be said to be a profound discovery. This has not yet reached consensual science, so you will be hearing this for the first time. I have been exposing my discoveries on YouTube for 4 years now. Actually, this is the anniversary month of 4 years of production, in which I have been able to produce over 1,600 videos, although I am far-ranging in my approach to science because I've grown accustomed to making these videos because they teach me. I began with the perception that I'm doing this for myself, which is somewhat contradictory because, of course, this is a public media platform. So that is not the whole story. But primarily, I do this for myself. I consciously embarked on this project with the intent to have a feedback system for myself, where essentially I learn from my own videos, which actually can be done. I found it to be consistently true, so I will say, based on my empirical research, it works. So this has been a success for me, and I am now somewhat enamored of this process, which I find hones my skills in all areas of research, presentation, cogency. I've learned to prepare and to use my tools better and better, so that now I am rather proficient compared to my my beginning status, which was not proficient at all. There have been some technological breakthroughs over the past 4 years for my small institute of one and the lab cat, who is actually quite critical. I live alone and have been since my wife died 18 years ago, and so I don't have a team. I don't have an affiliation where I have others to check my work. And that's actually quite an important consideration, because every scientist should have, if he can get it, a feedback system outside himself. This is somewhat artificial since I'm feeding back to myself. But that does work. I'm just quite impressed with at least the progress I've been able to make. This, of course, is relatively speaking. It doesn't mean that I'm a great presenter. We all have room for improvement, of course, and I don't think I've achieved any kind of maximum. However, there are thresholds of proficiency, and one by one surmounts the challenges and difficulties in presenting science in a way that is helpful to others as well as to myself. And I sincerely hope that my presentations help you in whatever way that might come about. The ideas that I present are not standard. Non-Euclidean geometry is exactly what it sounds like. It's not what is used in science. Science uses exclusively Euclidean geometry. We have faced, in this past century, really since 1900, with Max Planck's breakthrough discovery of a quantization at the physical level. That's where we get the concept of the quantum, which is a particle. And now there is a standard model for particle physics, as it's called, which treats everything in the universe as if it should be a particle. I doubt that the standard model particle physicists typically believe in their own model, because of course it's absurd. There is no way to structuralize the universe as if it were nothing but particles. Really, the system itself shows its flaw in what is conceived to be the graviton, which would be the quantum of gravity. This, of course, is a highly exposed topic now to the public because it's so fascinating. We're very interested, just as ordinary humans, with the progress of science at the cutting edge. This is the cutting edge, of course, the smallest things that can be called constituents of the universe. Historically, that was conceived to be the atom, which has undergone a change in definition beginning at the quantum revolution, it could be called. That was before the discovery of the proton. So it was a concept that Max Planck revealed when he discovered a fundamental relationship in energy transfer, that it must be quantized in order to be transferable. That is a perception, and it's not necessarily the best perception. The concept of energy quantization is now the cutting edge, as I said, but it's very difficult to quantize energy, because if you're quantizing energy, you have a unit. That has been shown, but it's a linear perception, where in linear perception, for something to be transferred, such as energy, it must be unitized, it must be quantized, it must be discretized, it has to have units. Because how could energy flow continuously and still be a quantity? You would have to be able to quantize it somehow in force units or pressure units or some kind of unit, or you can't measure it. It would simply be a wave. But a wave still could be quantized. When you draw a sine wave, that's essentially a linearized circular function. When the circle is exhibiting something moving, what is moving? Well, if you linearize that, it comes out as a sine wave, which basically shows on its descent it's going under, and as it reaches its peak, it's on the top. And so as it descends, it's going down the side, and when it reaches the trough, it's at its nadir. So it's showing a circular function that's been stretched. And that's quite useful. But it is composed of two units, wavelength and frequency. What makes that so interesting is that there are two different data types. So it's a correlation, actually a conjugation, of two quantized properties. The concept of continuity is not limited to that situation, where the continuity is the closure on the circle, which then has to be stretched in order to quantize the two related quantities, which appear on the curve, but they're related. They change in relation to each other. And this is usually called the sine component and the cosine component, whereby we get frequency and wavelength. What we want to explore is the concept of continuity, where it becomes paradoxical because you have to quantize the continuous action. And in fact, Max Planck's discovery was called the quantum of action. Later, very shortly thereafter, in the early 1900s, Albert Einstein was able to show that the transfer of light energy to a surface is also quantized, and that is called the photoelectric effect. It is then possible to say that light behaves both as a particle and as a wave. Ruđer Josip Bošković dealt with this contradiction. It's a contradiction. It can't be both a wave and a particle. What appears to happen, as best as we can formulate it, is that the wave quantizes itself into a particle. But how does it do that? That is called the collapse of the wave, and mathematicians prefer to add another word because that's a function. And so it's the collapse of the function. And the full term that you've probably heard is the collapse of the wave function, which Paul Dirac worked on basically his whole career and was unsuccessful. But it's very strange to talk about success or non-success when you're talking about a contradiction which by its very nature cannot be formulated in the language we're accustomed to using. So what appears to be happening, which I can now prove is happening, is that we are being called upon by a sort of an involute process to change our minds. We actually have to change our own perception. But that's very difficult to do, certainly for mathematicians, who literally can't do that. They can't change out of their linear perceptual space, and that raises a whole slew of philosophical issues having to do with consciousness. And the nature of the measurement problem, as it's called, has to do with this. You may have heard of the Schrödinger cat problem, which was formulated as an absurdity, and it was meant to be cruel. But it wasn't meant to be cruel to the cat, which is just imaginary. But the cat is said to be alive and dead at the same time in quantum superposition. And this led a man named Everett, I believe it was as far back as the 1960s, to come up with the ill-conceived, ill-named reapproach called the mini worlds, which should raise a huge red flag, or a bright red flag. Mini worlds? What do you mean world? Well, it's a direct assault on the paradox, such that he sort of inverted the problem such that he laid the problem at the feet of the universe, that we're seeing something that the universe is doing when it splits into two universes, one of which goes off into what would have to be called imaginary space, and therefore is never real again. But it was real for that tempuscule or moment, the indivisible unit of time in which the superposition occurred. Which is a very strange thing to say, and thereby I'm attempting to readdress the paradox in different words. But you can see that we're struggling for words. What Bernardo Kastrup has managed to introduce successfully, I am sure, into mainstream science is a purely philosophical reframing. He can't support what he says mathematically, but that may not be necessary, because it may be mathematics itself that's part of the perceptual problem, that we're using the wrong mathematical system, and that's where I come in. That is correct. So nobody yet, except for myself, apparently, has been able to prove where the syntactic problem lies, or you could even say the perceptual problem. The problem in formulating what is actually reality. So we are definitely in the philosophical room. The top room of science is the philosophy room, where we bring the discoveries of science into the human sphere to see how it affects us. That is the goal, although it's not usually formulated, I think, very clearly in the presentation of general science. What are we after? It's usually construed as technology, which is a huge mistake. To think of science as being only that, or even mainly that, it is not mainly that. It is mainly to get human answers to human questions. So today, just to close this off in the 3 minutes we have remaining, because I want to keep this to 20 minutes, as an introduction to continuity. And the list of terms over here is my approach to give us a jargon, an argot, a vocabulary for discussing this most fascinating, most engaging, most crucial problem that's ever been faced in science. I treat it as such. And I have made a series of extraordinary discoveries that deconvolves this extremely confusing and baffling issue of the relationship between quantization and continuity. Ruđer Bošković was the very first scientist to deal with this systematically. His breakthroughs are now being rediscovered, and I'm at the forefront of that worldwide team of scientists, loosely knit so far, who have rediscovered Bošković's work. In our exploration of continuity, we will begin essentially with Bošković, who lived about 300 years ago. He was a young man at that time, so he lived between 300 and 250 years ago, basically in the middle of the 1700s, right after Newton and Leibniz died. We will be talking about Newton, who is Bošković's predecessor, who dealt with continuity in the family of curves, an often overlooked part of Newton's work. And his work was in part based on his predecessor, Kepler, Johannes Kepler, who was the almost first scientist to explore the family of curves. My discoveries all relate to curvature, essentially circularity and sphericity. Not so much ellipticity, which is the description of a two-body system. That's why we have ellipses for the flights of planets, because it's a two-body system which has two foci of gravity. But in a proton system, you have a core made of one or more protons. We always reduce it to just one proton for geometric simplicity, but a proton makes a position in space and a spherical surface, which is a force field surface that inverts at its boundary. And that's essentially the radius of the proton, also raising the paradox again. But that's what Bošković dealt with. Thank you for tuning in to this station. You're in for quite a ride. Keep looking up. We'll be right back.